Hey everyone, and welcome back to my YouTube channel World of Electronics. In our last video, we acted as the master architects. We created the master plan, the detailed floor by floor, and got them fully tested. We ended with the crucial file, the Gate-Level Netlist. But a blueprint isn't a building. Today, the real construction begins. We are moving from the architectural office to the construction site. This is the world of back-end design.
But wait, before our construction crew can even break down the foundation, the safety engineers have a crucial job to do. They need to add a built-in testability plan. Why? Because our multi-million dollar chip is manufactured, we need to find a way to test it. You can't just go inside and see. In our analogy, this is like installing a fire sprinkler system or maintenance access tunnels throughout our skyscraper. This isn't part of living space, but these are essential for inspection and safety. In chip design, this is DFT. We insert special logic, mostly scan chains, which link all the storage elements together. This allows a tester easily to find manufacturing faults.
This highly specialized task requires its own power tools. They automatically insert the scan chains into our netlist and generate thousands of test pattern specific inputs designed to expose potential manufacturing defects. The main players here are Testmax, Tcent, and Modus from the big three EDA companies.
The engineers who do this are DFT engineers. They are the fault finders and they have a unique role working with both front-end architects and the back-end construction crew. To succeed here, you need to have a deep understanding on digital logic knowledge of different fault models and strong scripting skills to manage these complex flows. Okay, our blueprints has been updated. Now, before our construction queue start, they need the full set of instructions and materials. These are also, we can call them as construction recipe. They consist of four key ingredients. First one is DFT inserted netlist. This is our final approved architectural blueprint. The second one is technology libraries. This is similar to what we have done in the part 1. There also we have technology library. This is similar to them. Here we have the information of all the supply catalog and the exact physical dimensions in LEA file and timing and power characteristics in LIB file of every single cell. The third one is SDC. This is what we have discussed in the part 1. That is similar to that. Here also it consists of the information of PPA goals and client demands. Example, this chip must run in 2 GHz. It can't consume power more than 1 watt. And final one is initial floor plan. This is the architect's high level site plan, giving the construction queue a starting point for the layout. Before the first beam is raised, the crew lays the foundation. In the chip design, this is floor planning. Using our analogy, this is where the construction foreman stakes out the empty plot of the land, our silicon die. They decide where the main tower, our CPU core, and the parking garage, our memory will go. Crucially, this is also where the power planning will happen. We build a robust power grid. Think of this as an main power and water lines for the entire city block before building a single house. If this foundation is weak, the whole system fails. So what kind of heavy machinery does this crew use for this? The industry is dominated by three powerful place and route suites. The main players are IC Compiler 2 from Synopsys, Invoice from Cadence, and Aprisa from Siemens CDA.
The people responsible for this are physical design engineers. They are the site foremen of the chip world. To land this job, you need strong scripting skills, especially in TCL to control the tools, and a solid understanding of power integrity to ensure your chip's foundation is solid.
With our foundation ready, it's time to start putting the things in the place. This is placement. In our analogy, this is like crew placing millions of prefabricated components like the supported columns, the wall sections, and the window frames on each floor. The main goal is to place them as close as possible to keep the wiring short and fast.
Same tools handle this, but now we are using incredible complex placement engines. These aren't just dropping blocks randomly. They are timing driven, constantly calculating best position to ensure our chip will be fast enough.
Again, this is the domain of the physical design engineer. But to excel here, you have to be an expert in static time analysis or STA. You have to have a good understanding how every chip placement affects the final speed of the chip. This is one of the most important skills and jobs in the industry. Now we have come to the most crucial system in our skyscraper, the master clock. The clock is the heartbeat of our chip, and every part needs to hear it. If there is any disturbances or there is a difference between the clock timings, which is called a skew, it can cause the total chaos. So our goal is to make it as close to zero as possible.
The same three tools will be used here also as we used in the placement.
The structure is up, the critical systems are in, it's time to connect everything. This is routing. In our analogy, this is like massive electrical or data wiring phase. It's 3D puzzle on a massive scale. It is done in two steps. Global routing that which plans the main highways and the detailed routing draws the final streets to every connection point. The main tools here are the same as the CTS. The engineers who specialize here are expert puzzle solvers. They need a deep understanding of cell integrity, how signals can interfere with each other, and how physical properties of wires themselves can slow down the chip. Debugging the traffic jam or congestion is the key part of their job.
Now our skyscraper looks complete. But before we hand over the keys, it needs to go through series of brutal and non-negotiable inspections. This is sign off. The first is DRC, design rule check. This is checking against the factory's rule book. The second one is LVS, which means layout versus schematic. That means comparing the final layout to the original blueprint. And finally, the last one is STA check to confirm the chip meets its speed target with all the real delays of wire. The city inspector does not use the same tools as the construction crew. They have different specialized tools, high precision instruments to find each and every flaw. In the chip world, these are sign off tools, with Siemens caliber being the legendary gold standard. These are ultimate gatekeepers of your project. Physical verification and STA engineers are highly specialized and respected. Their job requires meticulous attention to detail as there is no room for error. They are final authority whether a multi-million dollar chip is ready or not. Now we have passed the inspection. The final step is to generate master construction file called as GDA file. In our analogy, this is like certificate of occupancy. Sending this file to the factory is called tapout. This is the final moment of our construction job is finally done. And a very quick note to my FPGA developers. When you click on implement in Vivado or Intel software, you are performing the entire backend and construction process. For planning, placing, and routing all automatically on a pre-built fabric of FPGA. You are using the same principles on reconfigurable skyscraper. And there you have it. From the architecture's dream in part 1 to the finished inspected skyscraper today. This is how a modern chip is designed. We have planned it, blueprinted it, built it, and inspected it, turning an idea into physical reality.
Thank you for watching. If you have any questions, let me know in the comments. And I'll be posting entire both front end and back end in my blog. If you have any doubts, there you can watch that later. Thank you.